Hello and welcome to this webinar hosted by Element 14. Today we're going to be talking about turning an electronic prototype into a product. With us, we're very fortunate to have Segi Segaran, an experienced professional in this field, who will be taking you through this fascinating topic. If you have any questions for Segi during the course of the webinar, please put it into the Q&A window and I'll make sure I'll ask it of him at the end. Without further ado, I hand you over to Segi Segaran. Take it away.
Thank you, Christian, and good afternoon to you all. And thank you to Farnell for inviting me to do this. I was delighted to be asked. So today's presentation, as Christian explained, was how to turn a prototype into a product. So let's get cracking. So pictorially, I'm sure a lot of you are engineers, and you probably all worked on products that ended up at some stage looking like these. And this whole presentation is about how to turn that into finished marketable products like these. There is possibly an alternative title for this presentation, and that is what they don't teach you on an electronics engineering degree. Now, certainly I didn't learn any of this in my degree. It took me years to get up to a stage where I could take a prototype into a product. And from what I've seen of graduates coming out of university, they're really expert at producing good designs, using the latest technology, particularly in software. But the gap is usually filled by industry. So with this information, hopefully, designers would hit the ground running. So who is it aimed at? It's aimed at anyone involved in electronic product design. For example, graduate electronic engineers would find it really useful following a good degree. Project managers who may not be engineers themselves would find some of the information in here quite useful. Small business owners launching products, and as we go through, you'll see that there is not much of a mystery here. The whole purpose of my presentation is to allow people who have possibly been sitting on projects to take it, run with it, launch it, and start making money. Some of this could feed back into electronic engineering degree content, and hobbyists who got the sort of breadboard prototypes that I showed earlier on and might be wanting to look at ways of turning that into a marketable product. Obviously, in a 45 minute presentation, I can't go too much into depth, but I'll touch on one or two design issues that, in my experience, always cause problems. Look at how to design for manufacture. Again, a very top-level overview of some issues to look at. Compliance. This often is a stumbling block to new engineers, and I shall try and give you a signpost as to how to navigate through this. And project management, actually making sure that the project is designed down to a cost and on time. So let's look at design issues. So a lot of you who have maybe working prototypes, a lot of degree students who in the final project here do a project as part of the degree course. I'm sure the design works really well, but they often use a benchtop power supply or a wall plug charger to get these up and running, which is great. They work, but often there is a need to integrate a power supply into the product. This may be for cost reasons, aesthetic reasons. Obviously, there are a number of reasons why I may want to do this. If obviously you can have a product that's battery powered, or still go to market using one of those power supplies, but even if you do that, there are some considerations to take into account. So I'm not shy. Let's look at some case studies, and this is just a generic picture I've used because this was quite a few years ago, and I couldn't find the right product picture to put in here. But this is one of I want to talk about areas where I've failed in the past as well as where I've succeeded, and this was one of my early mistakes I made as a junior engineer. So we had a product that used a built-in linear power supply, but the product had to detect very low-level signals coming from the distant end to transmit particular information, signals of around a few millivolts. What happened in actual fact when we put these out to trial was that variation in mains voltage, especially in rural locations, caused excessive ripple, i.e. noise on the power supply voltage, which resulted in non-detection of the signal, so failures in the field. Quite embarrassing for me. So how could we have sorted this problem out? It's instructive to look at how a linear power supply works very quickly. Mains voltage in, a transformer for isolation and stepping the voltage down. So this side is the hazardous voltage. This is the safe voltage side. Rectified, filtered, which is basically a very big capacitor, and regulated to produce a 5 or a 12 volt out for the electronic circuits. Now, this sort of power supply, a linear power supply, and I'm stressing the word linear because we'll look briefly at switching power supplies as well, is not very efficient. If the regulator has too low a voltage going in here, you can get excessive ripple. If it has too high a voltage, you can get excessive heat dissipation, resulting in overheating. What I discovered at the end of that period in attempting to fix this issue was an essential tool, which is a variac. Some of you may have seen this before, some of you may not, but I would say no good designer should be without this if you're using power supplies. So basically it takes a mains voltage in, and it's an auto transformer, so you can actually produce a higher voltage than comes in, and you can wind it right down to something like 190, 195 volts RMS to make sure that your linear power supply works and the product works over this range of voltages. Let me briefly mention switching power supplies as well. These are very efficient because they only take as much power as you need. They don't suffer from the same issues as a linear power supply. So there is a barrier with a transformer, but a much lower size transformer because it's working at a much higher frequency, opto-isolator, and because of this feedback mechanism, you only get as much, there's no overheating issues if it's designed properly. So let's have a comparison between switching and linear power supplies. Linear power supplies are quite bulky, switching is compact. Wide operating voltage range. So if you're designing products for an international market, a switching power supply is a good idea because they work effectively from 90 volts right up to 250 volts. So it's good. You don't have to change your designs for markets where the voltage may be 110 volts. Good efficiency, low heat dissipation. The slight disadvantage of switching supplies are high electrical noise and complex circuit design, not easy to repair. I have used switching power supplies and also external plug-top switching power supplies, but you have to be very careful with your sourcing because I've bought them and they've been specified at 5 volts, 1000 milliamps, and sometimes they don't meet the specification. So quick summary of power supplies, because a lot of products have fallen by the wayside because not enough attention has been paid to power supply. A lot of people assume it's a given, but if you don't pay enough attention to it, it can result in failures in the field. So subject power supplies to worst case testing. Some of you may be surprised, but the mains voltage in most areas of the world can change by plus or minus 15%. You'll be surprised at what products do when you run them down at around 195, 200 volts. And test at maximum and minimum current consumption to make sure there's no overheating or excessive noise. So quick overview on power supplies. I'm just going to pick up one other topic on the design side of things, which is tolerance. In my view, this is not dealt with adequately in a lot of courses. Not everything is what it seems. So if, for example, due to tolerance, if you look at a 100 ohm resistor, with a 5% tolerance, it could actually be 95 ohms. A 10,000 ohm resistor could be 9,500 ohms resistance. So all electronic components have a tolerance band. A few of you will be familiar with the resistor tolerance bands, 1%, 2%, and even up to 10% variation. Obviously, low power resistors you can pick up fairly cheaply at 1%, but if you're using power resistors, their tolerance is usually at 5 or 10%. So this has to be taken into account in the design, and particular attention has to be paid with variation in value with temperature, especially for capacitors. Again, let me give you a brief case study of a product I was involved in. This was a product for British Telecom, a caller ID telephone. It was designed for manufacture out in a factory in China by a Taiwanese firm, so truly international project. The prototypes worked fine. They were tested at Martlesham Labs near Ipswich, worked absolutely fine. We decided to do a field trial, so there was a small pre-production batch which worked fine in Penang when manufactured. Came over to the UK and failed during the field trial. The field trial happened to be up in Scotland in February, particularly cold cold winter. And when we analyzed the problem, it was down to temperature coefficient of the capacitors. From the factory to Scotland, Perth it was, so more than a 20-degree difference in temperature, which resulted in certain of the caller ID signals not being detected. But when we tackled this problem and fixed it, it became one of the most reliable caller ID telephones in the world, in the UK, I beg your pardon. So just to summarize on that, words of wisdom on that, just remember that what works as a prototype when you make only one, where you can adjust for tolerances, adjust the gains, and you think, great, I've sorted the problem. When you start mass producing it, when tolerance really comes into play, it might not always work. So it's worth spending a little bit of time on the design stage to make sure they iron out those tolerances. Just look at testing. Again, this is based on my experience with putting product out in the field. A lot of engineers are very good at functional testing. They make sure that the product works under normal conditions. What they're sometimes not very good at is worst-case testing. This is true of software engineers as well as hardware engineers. They assume everything is going to be fine. So really it pays to test product works on condition of the extremes of their possible values. This could be voltage, current, or temperature. And in my view, it's best if that testing is done not by the design engineer, but by another person who can be really objective when they're doing those tests. So really, in a sense, the failure we looked at earlier, such as the caller ID telephone and the alarm telephone, both of those would have been picked up under worst-case testing if we put them in environmental chambers. A couple of other examples on worst-case testing. Telephones, when they're in use, they actually work off line power provided by the pair of wires from your local exchange. The current that exchange supplies can vary anywhere between 20 milliamp and 80 milliamp depending on how far you are from the exchange. So if you're a kilometer from the exchange, it could be fairly high. If you're 5 or 6 kilometers, it could be fairly low. I've seen quite a few telephones which are functionally tested on somebody's line, and the assumption is, oh great, it works. But when it goes out in the field, mass-produced, if it hits a line where the current is only 20 milliamp, it'll stop working and then cause a lot of headache for the person who is charged to fix it. So this, I only take this as an example of making sure that the product is fit for purpose. Battery-powered units. Again, if you have a unit that's supplied from a power supply, then you've got a static 5, 12, or 3.3 volt to power it. But a unit that's battery-powered, the battery voltage is going to change. You might have, for example, a battery low threshold at 8.4 volts, and maybe get the unit to stop working at 8. So really from 8 to 9 volts, your measurement device, and this portable appliance tester has to measure accurately. You have to make sure that irrespective of your supply voltage being 8 up to 9, it has to give you accurate readings. So just some brief words of wisdom on the design testing side. Just spend a bit of time thinking about the operation of your product, where it's going to work, what sort of environment, what sort of temperature variation. Produce a design test specification, and use this at every stage of the product, and we'll cover that in a few minutes. And really the key point here is don't let the designer do the testing. Appoint somebody else to do this. I've seen this again and again, and it's happened to me as well. When I do the testing, I miss some of the problems with my own designs. If I get somebody else to do it, they tend to be far more objective. And if you find issues have been missed, then add them to the design test specification as the project progresses. Okay, so that was a brief look at the design issues. I'm sure there's a lot more to cover, but I've just covered the gaps that I've seen between an electronic engineering degree and what's actually needed in industry when turning a prototype into a product. Let's look at enclosures. For the electronic product. Sometimes considered last. So people tend to produce the prototype and think, oh, what sort of box shall I put it in, which is natural. And sometimes people do not take the cost of the box into account, just the electronics. And depending on what technology, what process you use for the enclosure, this can add significantly to cost. A good engineer, a good enclosure design can magnify sales though. So if you can get a good industrial designer involved in the design of the case, then that can pay dividends in increased sales. A good engineer will think of the whole product, electronics and enclosure, when turning a prototype into a product. Let's look at some examples of different types of enclosures. Injection molding is obviously your first choice if you're doing consumer products. Some of the issues with this tool can be costly. A design process has to be managed carefully because this can involve quite a few people, industrial designers, tool designers, the actual company producing the molding, and this can be in different parts of the world. So it has to be managed carefully to make sure. So people often concentrate on the final piece part cost, which is quite low for injection molding, but don't often factor in the cost of managing the design carefully. And also lead time for injection molded parts can be high compared to other methods. Ideal when manufacturing thousands of items, and certainly tens of thousands of items, and great for consumer products because the look and feel is good, and low cost of parts. So complicated, complex, but pays dividends in terms of a nice look and low cost. In my own experience, I've worked mostly on industrial products, not necessarily consumer products, and this has opened other options up for me in terms of enclosures. Custom plastic enclosures is quite a unique process. Certainly there are a couple of companies in the UK that provide this, and the starts off life as a single sheet of plastic. There's a groove cut in there and is folded up with some heat applied to soften the plastic, folded up at this end, CNC machined openings, CNC machine battery cover, so that's the top of the case, that's the bottom of the case of the battery cover, and the end product looks like this. Looking at the pluses and pros and cons of this approach, there's no tooling cost, there's just the design cost for the CNC machine. Made on the CNC machine using flat pieces of plastic, fast design. I've seen prototypes turned around in a week. Ideal when manufacturing low hundreds, but you've got a high cost of parts. So really on a low volume product, this could be an option where you don't want to bear the cost of injection molding. Certainly this product here we've been marketing for in excess of 10 years. We make it in fairly low volumes, about 100 per annum, and it still runs and runs for us. It's cost effective and brings us some money, which is good. Custom metal enclosures is also an option. Here we have an older product that I worked on. That's the top, that's the base, so bits of metal folded up to produce a case. And you can see why I say industrial enclosures, because as a consumer product this won't sell. But as an industrial product, function is more important than form, and as long as it's not ugly, people will buy it on the features. So again, this product here we don't sell anymore. We replaced it with another product, but did very well for us as a first product in the market. So we didn't want to fork out on a tool. So if you look at the pros and cons of this approach, it's very similar to the custom plastic approach. We chose metal here because we needed the strength. So low tooling cost. You might just need a die or two for the apertures that are stamped out in the metal here. Fast design process. Again, we've had prototypes turned around in a couple of weeks. Ideal when manufacturing low hundreds, and I think the pair of these cost us around £8 in the UK. Okay, that's high, but compared to the selling price of the product, that was well within budget. Finally, just a quick look at off-the-shelf plastic enclosures. Again, this is a product that we still sell. It's been selling for around 10-15 years. It's a caller ID product. Picks up the caller ID signal off the line and presents it to a PC. These off-the-shelf plastic enclosure, low tooling cost, just some slots machined in there for the sockets and the LEDs here. Machined on a CNC machine, fast design, ideal when manufacturing low volume and low cost of parts. I think, although I say low volume, this we make quite a few hundred a year. The enclosure costs £1 and the machining is £1, and there's just a 20p label that goes on top. So you can see it's very cost effective. Just some additional information with designing the enclosure. I said a good engineer will take the electronics and the enclosure into account when putting the two together. Disassembly for repair. Don't forget that products do break down. Even the best designed products do break down. And taking products apart easily is a good thing to bear in mind. So this is a product which was a nightmare to disassemble because there was sockets, switches, LCD in the top half, and then a PCB mounted in the bottom half with wires connecting the two. So to actually work on that board, you only had short bits of wires, and it was difficult to actually take apart. I think I'll have to speed up a bit. Whereas here I show you an enclosure which was much easier to work with, where everything, the socket, the PCB, and the mains input were all assembled in the top half of the case, the bottom half just acting as a lid. So choose the right enclosure for the job. For consumer products, injection molding is probably the right way to go for cost and appearance reasons. And just make sure that, for industrial products there are other alternatives, but make sure that the design is easy to disassemble for repair. On designing for manufacture, let's look at PCB technology as well, surface mount or through-hole. Obviously, surface mount has taken over from through-hole PCBs, and the majority of the boards we do are surface mount. But one shouldn't automatically go to that. It's got to be considered on a case-by-case basis. So, to give an example of the two, so here we have a surface mount printed circuit board where the components sit on top of the board and are soldered by infrared heat. They sit on some solder paste, which is then reflowed. Here we have components that go through holes in the board and are soldered on the other side, but you can see one surface mount component on there. So this is really mixed technology. Looking at the pros and cons of surface mount, it's great for manufacture, but it's a pain to prototype, as some of you will know if you worked with it, and hard to repair because some of the components on a very tiny pitch. Ideal for large volumes, for consumer products, easy to manufacture using machines, so production cost can come down, and ideal where sizes are premium. So on the through-hole side, easy to prototype, easy to repair faulty boards, and especially if you're exporting to less developed places where there's possibly only a soldering iron, etc. to repair boards, then through-hole may be the technology to go. Ideal for small volumes, but not all components can be machine assembled. Hand assembly is necessary, and the PCBs can be a little bit bigger. So don't always rush to surface mount PCBs. They're always the first port of call, but choose the appropriate PCB technology for the product. So here we come to the third topic, which is compliance. Let's look at electrical safety first, if it's mains powered. Some of this presentation is very EU-centric, but there are similar regulations in other parts of the world. The EU Low Voltage Directive, which then results in the CE mark, ensures that the user is protected from hazardous voltages. Just a brief look at that. There's a single fault principle, i.e. a single fault should not result in a user touching a hazardous voltage or a fire breaking out. So all electrical appliances that use mains voltage tend to have double protection. You can have a class 1 type construction where you have an earth and a basic insulation plus earth, or class 2 construction where you have basic and supplementary insulation, i.e. double insulation. I haven't got time to go into this in more detail, but these are the sort of issues that the designer will have to take into account if you're using a power supply. Inside, if you've got parts of the printed circuit board that are on the main side and parts that the user can touch, creepage and clearance is important. This is effectively the spacing between live parts and user accessible parts. So, for example, if that was a track, cross-section of a PCB track, it's going to a mains transformer, and that's on the other side of the transformer. That green line is a clearance, straight line through air, and the creepage is actually over the surface of the insulation. A bit technical, but just adding that for just give you a little bit more information to show that the layout of the printed circuit board is important. Rating plates, there is a minimum amount of information that you've got to put on there: voltage of operation, power, double insulation mark if it's class 2, any special warnings, and any necessary CE mark. There's a couple of examples there, which includes the wheelie bin, which is the WE regulations, waste electrical and electronic components, which we'll come to in a minute. Electromagnetic compatibility pretty much affects all electrical appliances that are made available for sale, is covered by the EMC directive, and is really designed to ensure interoperability of electrical products. So if you have a product that had emissions, standing next to a product that wasn't immune to those emissions, then you will have one of those products failing. So the whole concept of the EMC directive is to limit emissions from products and also to make sure that products are immune to interference from other products. So effectively, they work when they're put out into the field. And compliance to this is by testing to harmonized standards. So with EMC, you're looking at emissions, which could be radiated or conducted, and that is, for example, a listen, which is used for conducted emissions. And for the immunity, you're looking for immunity from RF fields, which could be radiated or conducted, fast transient burst due to switching, and electrostatic discharge. And there is an ESD gun that's used for that testing. So this is a specialist field, and there are test labs in most countries that would do this testing for you. And we'll look at how to take that into account at the design phase. Environmental compliance is increasingly an important part of launching products. The WE regulations, because there's so many products ending up in landfill, the WE regulations were brought in to maximize material recovery at end of life to prevent products from going into landfill and make sure they're recycled. That's actually, I think, a 15-foot tall man made out of waste products. That's the wheelie bin symbol we looked at to show, to actually try and advise customers not to put electronic products into the wheelie bin. Producers must register, and if you're in the EU, if you import into the EU, you're regarded as a producer and you must also register. Covers all electrical equipment, and the fee that you pay for registering is based on the weight of product that you place annually on the market. And the producer is also responsible for collecting and safe disposal at end of life, and they pay a fee for that based on how much they put on market. The ROHS regulations, the ROHS regulations, restriction of hazardous substances, have been in play for a number of years, and these are the substances that are restricted. Currently, people used to adapt the ROHS tick mark for that, but the legislation has been updated and it's a CE mark that's required now. So the declaration of conformity shows that a manufacturer has complied with the various harmonized standards. You've got to test against the harmonized standards, keep a technical file, prepare a declaration of conformity, and apply the CE mark. It sounds complicated, but once you understand the process, it's fairly straightforward. Let me finish off by looking at project management. This looks a little bit complex here, but I'll just go through some of the stages that's necessary to make sure that the project keeps to cost and time scale. So everything kicks off with a project brief. Sometimes people carry all this in their heads. It's good practice and good discipline to write it down. So the features that the product is going to have, what the target market is, what sort of budget we have for R&D, selling price, how many units we're going to sell a year. Now, if the marketing department or the marketing department part of your brain says we're going to sell 10 a year, well, surely you wouldn't consider injection molding. If you think you're going to sell 10,000 a year, then obviously you need to make sure that the budget is right for injection molding. Factory cost, obviously we're hoping for a good gap here. In our company, we try and go for a factor of 3. So we're going to sell something for a couple £100. We try and make the factory cost around, well, certainly less than 60, 70 pounds. That's in our industry. In some industries, the margins are a lot tighter. Product life, when do you have to replace it? And time to market, how long have you got? How much money have you got, and how long have you got to get a product to market? So these are important issues, and they will effectively feed into a project plan and a functional spec. So if you had the luxury of 2 people running the project, then that would be the project manager, and that would be the designer, electronic designer in charge. In a lot of projects I worked on, I've had both those roles to do myself. From the functional spec, the design test specification that we mentioned earlier, and a user guide. Now, it seems strange to look at a user guide before the product is designed, but in my experience, this discipline of doing a user guide early on is very useful, and it has brought out many issues earlier in the day rather than when the project's been designed, especially if there's software involved. So the project plan, we tend to go through stages, prototype, basically a rat's nest on a Vero board, alpha sample, which would utilize the first printed circuit board, and any outcome of the testing of that we would use to revise the PCB and produce a beta sample, and the enclosure designs feeding into both sample stage. So effectively, the design engineer's involvement in the project would come to an end at that beta sample stage. The project plan, of course, would continue to production, and if the company had a production engineering department, they would handle that. Or if you were subcontracting the design to an external OE manufacturing company, they would look after those stages with feedback back to you. I shouldn't need to stress the importance of field trials to you, based on the case studies that we looked at earlier. I'd rather see problems at that stage than when we've gone into the mass production stage. The design process itself, in a little bit more detail, design review is an important part of the process, and again, it's best to get input from senior experienced designers here. So from the prototype stage, test, produce a snagging list, i.e. a list of problems to be looked at, design review, feed that into alpha sample, use the alpha samples for some preliminary compliance tests, especially EMC, test again, repeat that process, and hopefully by the time you got to the beta sample, you got a product that's ready for manufacture. If that doesn't work, of course, you may have to reiterate that again and to go to another sample. I'll skip past this. Production documentation. Right at the end of the stage, when you hand over to production, be it within the company or outside, bill of materials, assembly drawings, final assembly, product test specifications, change control. This all important part. This is a production package that will have to pass on to make sure that the product can be mass-produced. In a lot of companies, this is done verbally and not documented, which is great if it's within the company, but when it comes to increased volumes, it will be impossible to do without having this documentation in place. Change control is important to make sure that any change that's done to the product is managed under ISO 9000, which is a quality standard. I see we've just gone past the 40 minutes, so which is good timing. Just a couple more slides to go. So I hope that's been useful. It's been a bit of a whirlwind. I shall give you directions to a couple of 2 or 3 books that may be of use to you to follow up on this presentation. What I've tried to do is dispel some myths. You do not have to spend tens of thousands of pounds to turn a prototype into a marketable product. I've worked on products where our budget's been a couple of £1,000s, apart from the designer's time, and we've turned it into products that we've sold directly to end customers. You do not have to manufacture in China. Certainly for consumer products, you may have to, but all our products we make in the UK, and we remain competitive. And you do not have to manufacture in the thousands to get a reasonable price. So if you choose your market and your product carefully and then manage your designs, you can still manufacture and market them at a profit. Electronic manufacturing is not just for large companies. Micro businesses, i.e. one-man or one-woman businesses, can manufacture and market products too. That's the book I launched back end of last year. It's available in print and ebook form, and it contains much of what I've gone through this afternoon. If you're interested in electrical product safety, that's an excellent book. It's a bit on the touch on the expensive side, but it's a great grounding in product safety. EMC, Tim Williams is a bit of an expert in that area, and that does cover a lot of relevant material. And on the industrial design enclosure side, I found Making It by Chris Lefteri quite useful. Well, I hope you found that useful, and I'll wait for Christian to inform me of some questions. Thank you very much.
Thank you very much, Segi. I'd like to start off with a question which sort of feeds into one of the questions that we have from one of our members of our audience. How have developments like 3D printing, the advent of single-board computers, lower cost processing power, how have those developments influenced the prototype to production process?
Thank you. Certainly 3D printing is a very interesting development. We've certainly looked at it for prototyping. We haven't used it yet. I mean, I'm sure other companies have used it successfully. I'm talking from personal experience. And one of the reasons is that if you recall the plastic custom enclosure option I mentioned earlier, when we were looking at an enclosure, even with 3D printing, you have to get the design done in a package that can then be fed into the 3D printer. And we didn't have the resources to do that internally. So if you had a design engineer who was capable of doing that, then that would have been great for prototyping. Costs are still high. You know, the boxes I was looking at, it took pretty much half a day to actually print those boxes. So it's great for prototyping, not sure whether it's great for manufacture yet. A single board computer, certainly we've produced internal products with the Raspberry Pi. And we are looking at 1 or 2 commercial industrial measurement products using the Raspberry Pi. So certainly speeded up the process for us.
Okay, thank you for that. One of the other questions that sprung to mind was the fact that you mentioned the whole project plan, and then you mentioned that during the process of generating a prototype, there's a point where the engineer hands off to another division, which will actually get it into production. If we've had a number of instances on the community in which there have been solo engineers who want to take their idea, their prototype into production. What are the differences that they have to take into account, and what advice would you give to an individual engineer who's trying to, say, take their product into production from out of their shed?
Okay. Again, a very relevant question. Let me answer that by giving a couple of examples from my own experience. SF Innovations, we produced a range of plug-in cards for the Raspberry Pi on the GPIO, using the GPIO, and it's a board-only product. There's no enclosure involved, and the low-volume stuff, the stuff we make, maybe 10 or 20 a month. Some of them I build, some of them I get a friend's son to build, and we. I like the fact that one person builds and another person tests. So if I build, somebody else tests it. If somebody else builds, I test it, and we market it straight from there. Products that are a bit more popular of those cars, where you have to build maybe 50 at a time, I've used a local CEM, contract electronic manufacturer, to take that into production. Does that help?
Yes, I think so. We have a question from Ansel Bagwandine. He's asking, are there different EMC standards for commercial versus industrial applications? Do you recommend acquiring a spectrum analyzer to do preliminary EMC testing?
Okay. They tend to be residential versus industrial applications. So if you have a product that is targeted to the residential market, the EMC standards for that is different to industrial applications. I wouldn't advise getting a spectrum analyzer unless you have some good experience in RF testing. If you do, then certainly a spectrum analyzer would help. But coupled with the spectrum analyzer, you need the right type of antennas as well. It's a very specialist field, and the people I use for that, they're not big firms. They're one or two man outfits that I use for testing. I don't tend to do those myself. They have years of experience, and when they spot an issue, they help me fix it as well.
Okay, thank you for that. We have a question from Matthew Lee. He's wondering what the creepage is for.
Okay, so imagine a printed circuit board on which you've got a transformer, a step-down transformer for your linear power supply. There's tracks on one side that come from the mains cable coming in, tracks on the other side, which is the low voltage side. The distance between the two along the surface of the board needs to be, is the creepage, and typically I work to something like 6 millimeters. If it was lower, if it was say 4 millimeters and you wanted to make it 6, you could put a little additional insulation on there. So the clearance would be line of sight, as it were. Creepage would be along the insulation, up over the wall, and then back down again. So it'll give you another 2 millimeters, if you like, to make up the difference. This is to avoid the electricity arcing across.
Okay, thank you for that. Do we have any further questions from the audience? Going once, going twice. Okay, I'd like to thank you, Segi, for this fascinating webinar. It's obviously inspiring some people to think carefully about how to turn their prototypes into production. And please stay tuned to Element 14 for more inspiration from Segi and others. And with that, I'd like to thank you. Oh, wait a second. We've got another question from Adrian Villerin. What good techniques can be used to do product life testing and determine the product warranty? That is a good question.
That's a difficult one to answer. I mean, warranty, you're going to have to offer 1-year warranty or 2-year warranty in Europe. So there's no choice. Obviously, you can offer extended warranty if you were confident with the life of your product. There is no simple answer to that. the parts which tend to fail are going to be the mechanical parts, really. So you could do life testing on that by rigging up some sort of actuator to operate the buttons, etc., to work out the life of the product. People may be familiar with the bathtub curve. For most products tend to fail in the first few days of operation. If they get past that, they tend to work, and then there's sort of failure when components start to wear down. So what a lot of manufacturers tend to do is to burn in the product. So after it's manufactured, they would put them on soak testing or burn in in a elevated temperature environment, actually operating to bring out any early failures. Products that go past that stage then can be put out into the field with reasonable confidence. There are ways of calculating MTBF, which stands for mean time between failures. Tends to be a bit of a theoretical exercise, and I personally don't use it myself. It's used a lot in high reliability industries such as flying and military.
Okay, thank you for that. Do we have any final questions before we wrap this session up? I don't think so. I think you've answered those questions very comprehensively. And so once more, I'll thank you again, Segi, for this great session. Like I said, it's been inspiring, and I'm sure that our engineers will take your words of wisdom to heart.
Okay, thank you very much. Thank you.
And thank you, everyone, and I'll say goodbye. Goodbye.
Goodbye.